Okay, let's get started. When an object moves at constant speed in a circular path, which of the following is true? One thing you have to know about circular motion is that even if the speed is constant, it's accelerated. And that's the centripetal acceleration, and the force that is necessary to provide that acceleration is the centripetal force. And what you have to know about it is that it is directed towards the center of the circle. So a net force pointing towards the center of the circle acts on the object. That we know is true. So let's see that the others are not true. The net force acting on the object is equal to 0, in which case it will be not accelerated, so that's false. Net force pointing along the direction of motion acts on the object. Now, the direction of motion is tangential to the circle, and if you have a tangential force, it will not move with constant speed. It will speed up in the tangential direction. Net force pointing away from the center of the circle acts on the object. Well, if it points away from the center of the circle, then it would not be accelerated towards the center of the circle. So that's false. Let's see, number 2. An object of mass 10 kg is initially at rest on a smooth surface. So you have a smooth surface and you have a 10 kg object. Now, a 100 Newton force causes it to move horizontally through a distance of 6 meters. So that's 6 meters. And you have a 100 Newton force. So there's a force acting on it, 100 newtons. Now, it's true that this problem is not well stated because we don't tell you that the force is horizontal, but it has to be in order for you to do the problem. Otherwise, you have to be told what direction. And you know that the question is, what is the change in kinetic energy? You know that when a force acts and moving an object, work is done. And the work energy theorem tells you that the work done, the net work done, is equal to the change in kinetic energy. Since they want this, the change in kinetic energy, all you have to do is to calculate the net work done. Now, with a single force, because the weight will be cancelled, the weight which is downwards will be cancelled by the normal force. So the net force is the applied 100 Newton force, and if they don't tell you the direction of the force, you cannot do it. So if you assume that it is parallel, that is horizontal, parallel to the displacement, then the net work done is F, 100 newtons, times by D, 6 meters, times by cosine of the angle, which is 0 degrees, which is 1. So it will be 6 times 100, which would be 600 joules. That would be the answer. Okay, number 3. 3 applied forces F1, F2, and F3. Now, it's not very clear. This is F2. So, act on an object of mass 2 kilograms, which can move along an inclined plane as shown. So, as a result, the object moves 6 meters, 0.6 meters along the surface of the incline in the upward direction. So, basically, you are told that is 0.6 meters. So, that's the displacement upwards. Now, they say if F2 is 40 newtons, what is the amount of work done by F2 as the object moves up the inclined plane? Now, work done by F2 is the force of F2, which is 40 newtons, times by the displacement, which is 0.6, times by the cosine of the angle between the force F2, which is, I'll put it in blue, it's horizontal. So the angle between the two vectors, if you look at this angle, they tell you it's 30 degrees here, it's 30 degrees here. So you know this is 30 degrees. So this would be cosine of 30 degrees. And if you go to your calculator, you work this out, it'll be 20.8 joules. All right, number 4, the problem is a 2.0 gram bead slides along a smooth wire. Now, smooth just means that you have no friction as the bead slides along this curve. And it says at point A, which is at the top here, the bead is at rest. So V is equal to 0 at point A. What is the speed of the bead at point B? So they want to know what the velocity is, what the speed is at the bottom. Now, what you do here is to use conservation of energy, because there's no friction and the normal force does no work. The net work done by the non-conservative forces would be 0. And therefore, what you have is conservation of mechanical energy, which is the easiest way to use that would be K at the initial point, which is A, plus U at the initial point. U sub A must be equal to K sub B plus U sub B. That would be the final position. Now, since at point A, your velocity is 0, therefore the kinetic energy at A is 0. Now, I'm going to pick, they tell you potential energy is 0 at this level. Therefore, the potential energy at point A would be M, which is 0.02 kilograms. I convert 2 grams to kilogram. G, 9.8 times by H, which is 1 meter. 100 centimeters is 1 meter. This must be equal to K sub B, which is 1/2 mass, which is 0.002 times by V squared. Sorry, I should erase that. Anyway, let's start all over again. So basically I have K sub A plus U sub A is equal to K sub B plus U sub B. So K sub A is 0, U sub A is M. Let me write that as M. G, 9.8, and H is 1 meter. This must be equal to the kinetic energy at B, 1/2 mv squared, plus the potential energy at B, which is 0. Now, what that means is you have mg times by 1 is equal to 1/2 mv squared. Now, you notice that I don't even have to know that m is 2 grams. They cancel out anyway. So this tells me that, let me move this up, tells you that v squared is equal to 2g, or v is the square root of 2g. And if you run to your calculator, it will work out to be 4.4 meters per second. Okay, on to the next page. Now, you are given that an object is pulled by a constant force 4 newtons for a horizontal distance 2 meters. See figure. So basically, this thing moves 2 meters. What is the work done? Now, admittedly, I put the two exams together, so this is repeated in a way to what we did before, but the work done by the force is just the force, which is 4 newtons, times by the displacement, which is 2 meters, times by the cosine of the angle between the displacement and the force. So this angle is 30 degrees. And if you run to the calculator and work out what those numbers give you, it is 6.9 joules. Okay, number 6, a mass is attached to one end of the string. The other end of the string is attached to the ceiling, so presumably that's where the ceiling is. The mass is released at point A and swings in a vertical arc to points B, C, and D, shown in the figure. Neglecting air resistance, at which point does the mass have the highest speed? Now, even if you include air resistance, well, it's not quite clear. It's true because you don't know how much energy you lose, so scratch that. Now, without air resistance, all you really have is conservation of mechanical energy. You start at point A with no potential energy because it's released at point A, and actually, even if it is released with kinetic energy, it doesn't matter, because what you see is that from point A to point B or C or D, you are decreasing potential energy from to B to C, and then you climb back up to D, you gain potential energy. Now, from energy conservation, if you lose potential energy, you must gain kinetic energy. So higher speed is highest kinetic energy, and highest kinetic energy, you will gain the most kinetic energy when you lose the most potential energy. And this would correspond to point C, because in going from A to C, you lose the greatest potential energy and therefore gain the greatest kinetic energy, and therefore the mass will achieve the highest speed. So that would be C. Okay, Pat and Joe meet in the middle of a lake while paddling their canoes. They come to a complete stop and talk for a while. When they're ready to leave, Joe pushes Pat's canoe and the force F is with a force F to separate the two canoes. Which statement is correct to say about the final total momentum and the final total kinetic energy? Now, initially, the two canoes are just side by side. And when they push off, you find that this canoe would move to the left and the other canoe would move to the right. Now, if you treat this as a whole system, then conservation of linear momentum, and linear momentum is conserved because there are no net external forces acting. As we discussed in class, the weight of the two canoes would be cancelled by the normal forces. And if you ignore the water resistance, then the net external force would be zero and momentum is conserved. And initially, the momentum is zero because they both have zero velocity. And conservation of linear momentum tells you that the final momentum, the final total momentum or final net momentum would also be zero. So P final is equal to zero. This is P net. Now, of course, it doesn't say that the velocity of each canoe is zero. As you know, one canoe is moving to the right, the other canoe is going to the left. So they have velocities. Their velocities may not be equal, but their momentum would be in magnitude. That's why they sum to zero. But if you look at kinetic energy, the kinetic energy of this canoe is 1/2 the mass of canoe 2 times by the velocity of canoe 2 squared. And this is positive, just like this canoe would have 1/2 m1 v1 squared. and it too would be positive. So when you sum two positive numbers, the final kinetic energy is positive. It cannot be zero. So you know the final momentum is zero and the final kinetic energy is positive. And if you go through all of the possible answers, the one that fits would be B. Final momentum is zero, but final kinetic energy is positive. All right, last multiple choice question. You have a 320-gram air track cart traveling at 1.25 meters per second, collides with a stationary 270-gram cart. They stick together after the collision. What is their common speed? Now, in collisions, linear momentum would be conserved. So you basically have something like that is traveling at 1.25 meters per second, and you have a second cart. This is 320 grams or 0.320 kilograms. This one is 0.270 kilograms, and this is stationary, which means that it is at rest. Now, after the collision, so this is the picture before collision. After the collision, they stick together and they move together. They move with some final velocity, which I call v. So let me move them up. The question is, what is their common speed after the collision? They stick together. Now, if they stick together, the two masses combine, so the total mass would be 0.32 plus 0.27, and if you need to use your calculator, you find it's 0.59 kilograms. So momentum conservation would say that the linear momentum before the collision, which would be the first cart mass, and if I call to the right positive, times velocity will be positive, plus mass, this is cart 2, times by its velocity, which is 0. This must be equal to the total momentum after the collision, which is the mass times by its velocity. So you have only one unknown here, and if you use your calculator and work out what v is, it works out to be 0.678 meters per second. Okay, let's get to the first problem here. Part A says, a block of mass 2.0 kilogram rests on a smooth table. It is attached to a spring with spring constant 300 newtons per meter. They say if the spring is stretched a distance of 1.2 centimeters, what is the resulting acceleration? So you have to draw a free body diagram. You have a block, and you can, if you wish, write down its weight, its normal force. I call it little n here. And if you attach a spring to it and you stretch the spring, this will exert a force, the spring force. And since it's on a smooth horizontal table, this is it. Now, we don't need to consider the vertical motion because it's not moving vertically, it's moving horizontally. And so horizontally, if you call that the x direction, Newton's second law, sum Fx is equal to m times by the acceleration, would allow you to figure out what the acceleration is. Now, what is the force? The force is the spring force, and the spring force is given by K times by x, where x is the extension or elongation or the amount of stretch. This must be equal to ma. So the spring constant is 300. X is 1.2 centimeters. Now you've got to convert to meters, which would be 0.012 meters. This must be equal to the mass times by the acceleration. So from the calculator, you can work it out. You'll find that A is equal to 1.8 meters per second squared. Okay, next problem. These are all little independent problems. Two crewmen pull a raft through a lock as shown. Now, crewman A pulls with a force of 130 newtons at an angle 34 degrees relative to the forward direction, while crewman B on the opposite side of the lock pulls with a force F at an angle of 45 degrees. Now, if you just look at the diagram, everything is there. That's essentially the free body diagram. If you abstract it and draw this as a point to represent the raft there. So if the raft were to move in the forward direction, that is, if it were to move in this direction and not hit the sides of the lock, what is the value of F? Now, for you not to hit the sides of the dock, that means you're not going to go this to that side or to this side. What that means is you cannot accelerate this direction or that direction. In other words, you have no acceleration in the y direction. So Newton's second law, which would be sum for the y direction, sum Fy equal to ma sub y, since we just argued that that's equal to 0, this tells you that the net force in the y direction is equal to 0. Now I'm calling this the y, the usual convention. That's the y direction. If you want, that can be the x direction. And if I wanted to find out what the acceleration is, I would consider what the x motion is. But in this case, I don't need to, because what this says is that sum of the y components of the forces would be equal to 0. And if you look at the force applied by A, then the y component is, well, the y component is this one. It's downwards. And it is opposite the angle, the 34-degree angle. So the y component would be F times pi, because it's opposite, it's sine 34 degrees. Now, because it's downwards, the component is negative. You add to that the component, the y component of the other force, which is the unknown. And once again, it is opposite the 45 degrees angle. And now it is positive, so I plus a positive thing. It is positive, and this sums to 0. And you can simply use the calculator and work out what F is. And it turns out F is equal to, now this is to two significant figures, because the angles are two significant figures. So it works out to be a little over 100 newtons. So I round it to 100 newtons. Okay, the last part in this problem relates to this figure. Now, in the figure shown, block A has a mass of 5 kilograms and block B has a mass of 3 kilograms. Now, the coefficient of kinetic friction between A and the table is 0.4. Calculate the acceleration of the blocks and the tension in the rope connecting A and B. Okay, so this is a problem application of Newton's second law. And to do that, you always draw free body diagrams. Now, there are two free bodies, so let me draw them both. The first one, let me look at B. All right, so this is B. You know it has a weight, 3G, and the rope that is connecting it to the pulley and then to A, and that rope has a tension. Now, the weight B is going to move the system, and it's going to have an acceleration downwards. Now, if you apply Newton's second law to this free body diagram, you would say if I call downwards the positive x direction, then sum fx equal max gives me 3g minus t is equal to 3a. That's all you can write down. You have two unknowns, so you can't solve this. Let's go to the other problem. Now, the other free body diagram is A, and it has tension, same tension as this, as the one that is in B. So it's the same T as that because it's one rope here. And you have the weight of A, which is 5g. Because it's in contact with the table, it's got a normal force, I call little n. And because it is rough, there's a coefficient of kinetic friction, and this body is accelerating to the right with acceleration a. Since it's moving to the right, there is a friction force, and this is kinetic friction. So that's the free body diagram, and if you were to apply Newton's second law to the x motion, it says sum of x components. So only t and f sub k have x components. It would be t minus f sub k, because friction is in the negative direction. You add a negative number, you subtract f sub k. This must be equal to the mass, which is 5 times by its acceleration. Now, you also know from the, let me put that in blue, you know it's not, the block A is not moving up or down. So its y motion has 0 acceleration. So sum Fy is equal to 0, which means that n minus 5g is equal to 0, or n is equal to 5g. Now, why do I need to calculate n? Because you know that kinetic friction is equal to mu sub k times by the normal force. And now that you know n, you can work this out. Mu sub k, the coefficient of kinetic friction, is 0.4, and n is 5g. And actually, if you take 0.4 times by 5, you work it out. This is equal to 2g. Let me get more space. Okay. So with this, I can now go back to this equation, and I'm going to write it in black. So it says t minus 2g, which is what f sub k is equal to 5a. Now, this equation in black and this equation, you now have two equations and two unknowns. You can solve them. Now, there are many different ways. One way is you can write them side by side, one on top of the other. I'll write the other one here. 3g minus t is equal to 3a. Now, of course, you can use this equation and you say, okay, if I bring t to the right-hand side, now it's on the right-hand side, and I bring 3a to the left-hand side, I know t, and now I can substitute t into this equation and solve for a. I can do that, or another way is by writing the two equations like this. I can add the left-hand side. So this is the left-hand side of both equations. You have t minus 2g plus 3g minus t. So t minus t go away, and 3g minus 2g, you get g. And if you add the right-hand side, it is 8a. So a is 1/8 g. Now you can use the calculator and work out a number, but if you leave this as the answer, it's perfectly acceptable to me. More space. Okay, once you know a, you can now work out t. Now you can use this equation or this equation. Either one will give you the same answer. If we use the top one, it says t minus 2g is equal to 5 times by a, which is 1/8 a, which is 5/8 a. sorry, A is 1/8 G, so this is a G, so this is 5/8 G. So that means T, you just bring the minus 2T to the right hand side, it becomes plus 2G, and you get 2 and 5/8 G. So that's your tension, and this is your acceleration. Okay, next problem. You're given an object of mass 2.5 kilograms is at rest on a smooth inclined plane with height h, length 8, and which makes an angle of 30 degrees with the horizontal. So this is given in your sketch. So basically you're told this is height h, and the angle it makes with the horizontal is 30 degrees. So this is a right triangle like that, and this is 8 meters here. All right, this is smooth inclined plane. All right, so they ask part A, find the height h via geometry. So this is basically looking at this triangle, and you notice that h is opposite this angle. Therefore, you know that the sine of 30 degrees is opposite over the hypotenuse, which is 8. Therefore, h is 8 times by sine 30, and you work it out, it will be 4.0 meters. Okay, part B. It says, the object slides down the plane. What is its speed when it reaches the bottom? Now, it is at rest on the inclined plane. So it is starting at rest at this point. What is its speed? Okay, once again, the easiest way to do this is through energy conservation, and which states that the kinetic energy at the top plus, so I call that initial, plus the potential energy at the initial point is the final kinetic energy plus the final potential energy. Now I'm going to call this the zero of potential energy, gravitational potential energy. Therefore, the initial kinetic energy is 0, and the initial potential energy is m. It's 2.5, but I'm going to call it m g times by h, which we know is 4 meters. Oops, this is equal. All right, equal. So the final kinetic energy we do not know. It is 1/2 mv squared, and the final potential energy is 0. Okay, and so once again we have the usual thing. The m's cancel. I can divide both sides of the equation by m. That's how I cancel them. And if I multiply both sides by 2, I will get v squared is equal to 8g. So v would be the square root of 8g, and if you were to go work it out, you would get an answer that is equal to 8.9 meters per second. Okay, remember the picture. It says that the horizontal surface at the bottom of the inclined plane is rough. So this patch of it is rough. All right, it's no longer smooth. It tells you that the work done by the friction force on the object on sliding the first 4 meters is minus 53 joules. So you slide this distance. In sliding 4 meters, the work is minus 53 joules. Find the speed of the object after sliding horizontally for 4 meters. Now this one, because you now have a non-conservative force acting, you have to use this. The work done by the non-conservative forces must be equal to the change in kinetic energy plus the change in potential energy. So you are told the work done is minus 53 joules, and the kinetic energy change just means 1/2 mass. Now the mass is 2.5 kilograms. It will be V final squared, don't know what that is, minus 1/2 mv initial squared. So I'm going to factor out the 1/2 m, so minus v initial squared. Now v initial squared is this, because at the initial point, which is at the bottom of the ramp here, it will be traveling with a speed of 8.9 meters per second squared. And so v initial squared is this v squared. So you know it is 8g. Or you can put 8.9 squared, it doesn't matter. So this is the change in delta K plus the change in, so this is delta K, the change in kinetic energy. Now the change in gravitational potential energy, I hope you can see that's zero. There, at the bottom here along the horizontal, there is no change in height, so there's no change in gravitational potential energy. Okay, so from here, you can just solve for V sub f. This is just algebra. Remember, if you don't do anything and you write just this equation in the exam, you'll be getting 90% of the score. Anyway, if you put this in and you work it out, you will get 6.1 meters per second. That's the velocity. Okay, part D says, from the work done by the friction force given above, find the force of friction. Now you know that the work done by any force is given by F times D times cosine of the angle between them. So for the friction force, you just use the force of friction, which you do not know, so it's F sub k, it's kinetic after all, times by the distance, which is 4 meters, times by the cosine of the angle between them. Now in friction, the angle is always 180 degrees, the angle between the friction force and the displacement, and cosine of 180 degrees, this is equal to -1. But in part C, you are told that the work done by the friction force is minus 53 joules. So this is equal to -4 F sub k. And working this out, you get F sub k is equal to 13 newtons, the two significant figures. Now finally, you have this part. It says, what is the coefficient of kinetic friction between the object and the horizontal surface? So you know the force, the kinetic friction. But you know that kinetic friction is also equal to mu sub k, the coefficient, which is what you want to find, times by the normal force. So in order to use this to solve for mu sub k, you have to find the normal force. And if you draw the free body diagram, as it is moving, you have the weight, 2.5 g, you have the normal force, and it is moving to the left. The friction force is to the right. But in this case, you don't care, because sum Fy equals MAY equals 0 would tell you that N minus 2.5 G equal to 0, or the normal force is 2.5 G. So you can now put this into this equation. Let me write it in red, create more space. So what you have is 13 equals to mu sub k times by 2.5 g, and mu sub k you can solve this out to give you something like 0.53. Okay, last problem. Now this is a problem on collision, elastic collision, and this is actually rather challenging if you try to solve it without using something that you will see in class. So the problem is as follows. Two air carts with masses 2m and 3m are placed on an air track. The 2m cart is traveling at 2.5 meters per second to the right, which is the positive direction, and collides with the 3-meter cart. Part A says, if the 3-meter cart is stationary and the collision is elastic, what are the speeds of the 2-meter cart and 3-meter cart after collision? Now, there are two ways to solve this problem. What you find is that this is what is given in your book. All right, what is given in your book is the following. It says that if you have an elastic collision in one dimension between a moving cart and a stationary cart, and the picture that they'll give you is you have a cart that is moving with velocity v0, and you have another cart that is stationary, so this is not moving. All right, so this is M1 and M2. And after the collision, after the elastic collision, M1 would be moving with velocity v1, and M2 would be moving with velocity v2. Now you would see this in class. Between conservation of linear momentum and conservation of kinetic energy, which is what the elastic collision means, you will have those two equations, and using those two equations, you can solve for v1 and v2. All right, and your text actually call this v sub 1 final and v sub 2 final. And there's just a simple formula that is derived. It says v sub 1 final is equal to m1 minus m2 over m1 plus m2 times by v0, and v sub 2 final is equal to 2m sub 1 over m sub 1 plus m sub 2 times by v sub 0. So if you have these two formulas given to you, it's very simple. This first part is very simple. And all you do is you identify what m1 and m2 are and what v0 is. So if you read the problem, you'll find that m1, which is the first cart that is moving, has mass 2m. m2, which is the stationary cart, has mass 3m. And then you have 2m plus 3m, and v0, you're told, is 2.5 meters per second. And if you were to work it out, 2m minus 3m would be minus m. 2m plus 3m is 5m. Minus m over 5m, you can cancel the m, you get minus 1 1/5 times by 2.5, which works out to be minus 0.5 meters per second. Now, you can do the same thing for, this is the final velocity of the first cart, okay, m1. Now the final velocity of the second cart is 2m1, which is 2 times by 2m, so that is 4m, and m1 plus m2, which is 2m plus 3m, is 5m, and v0 is 2.5, and the m's cancel, and 0.8 times by 2.5, you'll find that is equal to 2.0 meters per second. So those are the two answers. Now, unfortunately, part B is a lot more challenging because it is once again an elastic collision. So now, instead of being stationary, the 3m card is moving to the right. So now it is a little bit more difficult, unless you see something that I will present in class, which is in an elastic collision, you can derive this formula. And this formula can be written this way. So I will start out once again. Now you have two objects, m1, and it is moving with velocity v1 initial. And it collides with another object, m2, which is moving. Now, this is a vector. I don't even really care what direction it is. I'll just write it as a vector. This is v2 initial. Okay? And after they collide, you have a similar picture. You have m1 and m2. And they will be both moving, and you don't have any idea. In fact, I don't have to draw the arrow indicating the direction. All I need to know is that it's got some final velocity. Sorry, so this should be 1 here because it refers to m1 vector. And this one is moving with v2 final, v sub 2 comma f. Now, if you apply conservation of linear momentum and conservation of kinetic energy, you can show that there's a very simple relation between these four velocities. And this relation is as follows. Let me write it in black. It says v sub 1 initial vector minus v sub 2 initial vector must be equal to v sub 2 final vector minus v sub 1 final as a vector. Now, if you know this, then the algebra works out to be rather simple. And even then, because I have to write so big, it's going to take out a lot of space. So reading this problem, m1 is 2m, m2 is 3m, v sub 1 initial is the 2.5 meters per second. You can read the question. The v sub 2 initial, you're now told it is moving, the second card m2, which is of mass 3m, is actually moving to the right at 1.2 meters per second, so it's no longer 0. And v1 final and v2 final are the unknown velocities after the collision. So if you put this in, if you call to the right positive, then v1 initial is 2.5. If you want, you can indicate the direction x hat minus v2 initial. It is also it is also moving to the right, so it is positive 1.2 x hat. So this is equal to v2 final minus v sub 1 final. And what 2.5 minus 1.2 is 1.3 x hat is equal to V sub 2 final minus V sub 1 final. Incidentally, you can apply this formula to solve problem 1. In fact, you might want to go back and try to use this to solve problem 1 in exactly the same manner I'm solving problem 2. Now, this one is one equation in two unknowns. I have to find another equation. So the other equation comes from momentum conservation. So let me get more space. Momentum conservation is as follows. It says the momentum before collision, which is you have the 2m, that's the mass, multiplied by its velocity, which is 2.5 x hat. You add to it the momentum of the other object, which is 3m, times by its velocity, which is 1.2, it's positive, x hat. This must be equal to the momentum after collision, which is the mass 2m times by the final velocity, which is v sub 1 f, plus the mass of the second card times by its final velocity, v sub 2 f. And from here, you can divide both sides of the equation by m, and it turns out what the value of m is immaterial. Okay, so let's see. What I'm going to do is multiply the left hand side. 2 times by 2.5 is 5. 3 times by 1.2 is 3.6. This must be equal to 2v1 final plus 3v2 final. So what I can do is to divide both sides by 2. Now, there's no rhyme or reason for that, except it helps me solve the problem. So 5 times plus 3.6 is 8.6. You divide by 2 is 4.3. And on the other right-hand side, if you divide by 2, you get v sub 1 f plus 1.5 v sub 2 f. Now, there are many ways to solve it. If you actually can write down this equation and this equation, like I said, you'll be getting 90% of the points. Now, the reason I do this is because I can solve this two equations, these two equations. Because I have two equations and two unknowns, I can solve for v sub 1f and v sub 2f. And the way I'm going to do that is I'm going to write this equation down below. Right below it is equal to v sub 2f minus v sub 1f. Now you can see why I divided by 2 and reduce the equation down. I divided by 2 here, right? To get this equation. I divided by 2 here to get this equation. Because you notice that I will do the same trick before. I'm going to add the left-hand side, which will give me 5.6. And if I add the right-hand side, I have v1f, this term, and I have minus v1f. So when I add these two terms together, they cancel. I have 1.5 V2F and I have 1 V2F. So 1 plus 1.5 is 2.5 V sub 2F. So from here, V sub 2F is equal to, I divide both sides by 2.5, and when I do that, I'll get 2.24 meters per second in the x-hat direction. Now, once I have this, I can use either equation to figure out the other unknown, V sub 1F. So let me use this equation. So this equation, I'm going to bring V sub 1F to the left-hand side. So minus V sub 1F, bring to the left-hand side, it becomes plus. And it's equal to V2F, this term, which I know is 2.24 x-hat. And then this term, I move to the right-hand side, it is minus 1.3 x-hat. So now you can see I can work out what V sub 1F is, and it turns out it is 0.94, and 0.94 is really meters per second in the x-hat direction. So after the collision, both cards move to the right. The second card moved with a higher velocity than the first card. Okay, the bonus one, you can just work it out yourself. I've run out of space. It's not so bad. The bonus point problem asks for the impulse delivered to the 2M cards because of the collision. And all you have to do is to remember that impulse is equal to the change in momentum. And this refers to the 2M card, so you just have to find the change in momentum of the 2M card, which is 2M times by the final velocity minus 2M times by the initial velocity. And if you work this out, it turns out it's minus 3.1 times by M. This you have to know what M is in order to get a numerical answer. But if you don't know what M is, that's what it is. So you have minus 3.1 M and x-hat. So if they ask for the magnitude, it will be 3.1 M kilogram meters per second, and the direction would be in the negative direction. Now that shouldn't surprise you, because you know that the 2M card, which is M1, it slows down. For it to slow down, you have to apply a force in the opposite direction. So it is in the negative direction. And of course, the impulse is in the same direction as the force. And hence, you can understand the negative. Okay.